Very good afternoon and warm welcome to this live session. So I am Dr. Vaibhav Pandit and today we are going to discuss the topic that it is titled here magnetic flux density, and this is the topic belonging to the subject electromagnetic field theory. So this is our 14th live session to solve your doubts related to the various topics belonging to the electromagnetic field theory, right from the understanding of the coordinate systems as like the rectangular coordinate system, cylindrical coordinate system, then the spherical coordinate system, along with the knowledge of the vector operator known by the del, gradient divergence and curl operation. We have entered the electric field understanding and then the magnetic field understanding, both at the static condition here. So today's topic magnetic flux density, this is one of the parameters that describes the behavior of the magnetic field. So the study of magnetic field as well as the electric field we have to carry together, and that it will form the electromagnetic field basically of the wave nature, and further we call it to be the EM wave in abbreviation here. So this is our topic. So here we take the magnetic flux density, the topic title, and I can get your concept clear with the help of the illustration. So in the illustration I will show you first of all the source of the magnetic field, because instead of understanding first of all the magnetic flux density, what is magnetic flux density, you should have a knowledge of what exactly the first two terms mean, magnetic flux here. See, as we are already covered with the topics related to the electrostatics here, so I hope you are clear with the concept that the electric field is in existence wherever there it is a charge in static condition, and when the charge is in motion, so that time we call the flow of charges, it means a current here. So the current, it is nothing but the source of magnetic field. So wherever there it is a current component, there it is magnetic field. Now whenever we talk about the terms related to magnetism, the first picture comes to our mind that it is a bar magnet here. So here you just visualize a bar magnet where the two ends are the two poles of this magnet designated by the capital N and capital S respectively, showing the north pole and south pole here. So even into the science subject in your school days you have learned that there are certain lines of forces that originate at the north pole here, and they are making the circulation and they are ending, they are terminating onto the another end that it is south pole. So this is the one thing, from north pole the lines get originated, lines of forces, and they end upon the south poles. So these are nothing but the flux lines, these are nothing but the flux lines. So as the flux lines are associated to this particular magnet, it depends on how much the magnitude it is carrying. So those many number of flux lines are originated from the north pole here. So this is just the representation of the general magnetic flux here. Now coming to the exact point for analysis purpose. See, the magnetism can be produced by the current carrying element as well. So let us have another illustration where we have a metal rod, and through this metal rod we are having a flow of current. So let us say from bottom end to the top end the flow of current is directed. Here it is shown I. and this is somewhat the upward direction of flow of the current here. So where is the magnetic field? So magnetic field is there into the surrounding. Simply we can define that whatever the surrounding region that it will be under the influence of the current carrying element. So thereupon we have the magnetic field, and the existence of the magnetic field is validated by the several of the experimentations made by the scientist, for example Faraday here, whereupon the existence of the force of the lines carrying certain kind of force is there, and here in this case it is the magnetic flux. So whatever the two lines those are circulating around this current carrying rod here, this is nothing but the magnetic flux here. So as I have already covered the concept of magnetic field intensity, so intensity is just a parameter to describe the strength of the source of a certain field. If the magnitude of current flowing through the conductor is more, so that time the intensity, the strength of the magnetic field will be more. So we have the representation of magnetic field intensity denoted by capital H, that we have practiced a lot in our previous videos here. And now here the magnetic flux density is another term that it is associated with the same magnetic field here. We can derive the magnetic flux density from the magnetic field intensity just with the help of one constant here. So that will I definitely explain you people. Now just keep one thing in your mind: the magnetic flux density throughout this lecture and in our subject electromagnetic field theory is denoted by capital B. Now the question to your mind, whether this is a scalar quantity or a vector quantity. See, this is a vector quantity. It has the magnitude, it has the direction as well here. So this is one just the illustration where the right hand thumb rule is used to determine the direction of the magnetic flux surrounding to the current element here. See, if current is there in the upward direction, you just have your thumb in the direction of the current. The curled fingers, the four fingers will be curled here, will give you the direction of the circulation of the magnetic flux lines here. So if current is there in the upward direction, here the curled fingers will give you the direction of circulation of magnetic flux lines here. Same it is also illustrated in this expression also. And when we measure the density it means how many number of the units for a specific quantity we measure for a certain limited length or the surface area or the volume, correspondingly it gets to density here. So this density is with respect to the surface area here. This is not with respect to the length, this is not with respect to the volume, but the surface area, the two-dimensional case here. So whenever we have a certain plane, and through this particular plane that it is having a certain area that I can show with the shaded portion, how many number of magnetic flux lines are crossing it. They are penetrating from one end and going outside from the back side here. So if we have a count of all this is nothing but the magnetic flux density. It is a vector quantity and it is denoted by capital B. Now a similar kind of parameter we have also learned in the electrostatic section. Thereupon it was electric flux density. Whenever there it is a positive charge, it will originate the electric flux lines and they will terminate onto a negative charge. So those lines of forces are electric flux lines here, whereas these are the magnetic flux lines here. Now what was the symbol to denote the electric flux density? The symbol was capital D. And what was the symbol to denote electric field intensity? It was capital E. The relation I give you, see, we used to have the measurement of the electric flux density denoted by capital D by making the use of electric field intensity. Now you see D is equal to epsilon 0 times E. See, the not 0 here is just to represent whether the surrounding medium is air or vacuum or simply free space here. So epsilon here it is permittivity of the medium here. So permittivity, how much the given medium is permittive to the flow of electricity through it. So it is measured in terms of farads per meter. So here also, as we have the knowledge of magnetic field intensity, now for the magnetic flux density we have the relation, and that relation here it is capital B is equal to mu 0 times capital H. So here also the consideration is that the surrounding medium is there a free space or air or the vacuum here. So our today's topic, magnetic flux density, this is a quantity, this is a parameter to describe the magnetic field. Here it is denoted by capital B, and capital H is magnetic field intensity that we are already covered in our previous live sessions. Now see, these are related by a constant denoted by mu 0. Mu 0 is permeability of the medium. It is measured in terms of Henry per meter. See here, epsilon 0 is permittivity of the medium, and that relates the electric flux density with electric field intensity, whereas mu 0 is permeability of the medium, that relates magnetic flux density with magnetic field intensity, and both of these values are constants here. Now more information with respect to this particular value when the considered medium is a free space. So that time mu 0, the constant value is 4 pi into 10 raised to the power minus 7 measured in terms of Henry per meter here. Now what is the use of this magnetic flux density? See, whenever we are having the knowledge of or the value of magnetic flux density in a certain number here, so using the flux density we can have a calculation of the total amount of magnetic flux leaving a certain surface area. And as far as your examinations are concerned, mostly the problem statements are as such that you have been provided the magnetic flux density or the parameters with which you can have the calculation of the magnetic flux density, and using the magnetic flux density, if you carry out the integration over a certain surface area, you will come to have the computation of total amount of magnetic flux that is crossing that particular surface area. Now see here, the total amount of magnetic flux can be denoted with the help of the symbol. The symbol here it is phi here. So phi represents the total amount of magnetic flux, and it is measured in terms of Webers. So Weber is the SI system of unit for the representation of this particular magnetic flux here. Now see here, it is obtained by just having the surface integral B bar dot of ds bar here. So what is B bar? B bar is the magnetic flux density. What is ds? It is the differential surface area. So when we have the dot multiplication of the two vector quantities, see here B is a vector, magnetic flux density is a vector, ds differential surface, though it is a surface, its perpendicular direction will also be very important for us. So magnitude as well as the direction, it will of course be a vector. So for both of these vectors we will have a dot multiplication, and the resultant we have to integrate over a surface. That is why in the suffix to this integral notation we have denoted s here. So of course this will be a double integral. The surface integral means a double integral here. Now as I have just compared the relation of the magnetic flux density with magnetic field intensity, similar to that we have already seen electric flux density to electric field intensity just by the constant, a change of notation and the change of course the constant value here. So thereupon we used to have computation of the total electric flux by using this electric flux density, and thereupon we had the expression. So in this expression we have denoted psi as a function to denote the total amount of electric flux. So in our subject just have the differentiation here of the quantities here. the psi is denoting the electric flux, total electric flux, whereas phi is denoting total magnetic flux. Or sometimes psi suffix e represents electric flux, psi suffix m is also utilized as a representation symbol for magnetic flux here. Now the thing is, both we are obtaining by the integration over the surface. So electric flux we are obtaining just by integrating d bar dot of ds. So d is electric flux density, whereas phi we are obtaining just by integrating b bar dot of ds, but there is a difference in both these integrations here. Now in the case of electrostatic, to carry out the computation of total amount of electric flux crossing through a surface area, certain area, the integration is over a closed dimensions here, so that it was a closed surface integral, whereas it is not the closed surface integral in the current topic magnetic flux density here. So that is what the change, because the source of electric field is a simple static charge. So if this is a point here, I draw a point here, and if it is having a positive magnitude of certain charge in terms of coulombs here, so that time it will originate the electric flux line in all the possible directions into the surrounding. So this is nothing but the divergence physiological operation that we have learnt in the first chapter here. So it is just expansion if we are considering a positive magnitude here, and if we are considering a negative magnitude, so that time the lines will come from the infinity, in general we say from other locations, and they will end upon that negative charge. So this is just the contraction, the expansion of something and the contraction of something. So this is just representation of the divergence phenomenon here. Whereas in the case of the magnetic field, if we are having the current carrying element like this and the flow of current in the upward direction, the circulating lines are there surrounding to this conductor, and this is just the representation of the magnetic flux lines. So magnetic flux lines are not showing any kind of expansion or the contraction here, whereas they have a circulating nature that can be represented by the curl operation in the mathematics here. So that also we have covered in our first chapter here. So because of this particular circulation, we need not to have any closed surface here. Any surface that you put in this particular illustration, so if you count how many number of lines are crossing this particular surface, this surface is of course not the closed surface, it is open surface. So the surface integral will be a simple surface integral. It will have the different limits, lower limit and upper limit will be a different, and when the limit is same, so that time it will be a closed integral. So that is what the difference when you compare the things from electrostatics and from the steady magnetic field here, I can say. Now as we see here, the circulating lines are there. So from any point if you see, the line is making a revolution and coming back to the same position here. So therefore if we have the closed surface integral of b bar dot of ds bar, so it will be resulting into 0 here. So the net amount of magnetic flux will be equal to 0. That is why we don't have the integration over a closed surface here, because the closed surface, it will be having the two faces here. From one face the magnetic flux line will enter into a certain volume that has been enclosed inside that closed surface, and from the another end it is supposed to go outside here. So positive negative it will cancel out, and you will be resulting into the value total or the net flux enclosed inside a closed surface is equal to 0 here. So this is the way of representing this thing, this observation, by the integral notation here. So closed surface integral b bar dot of ds bar is equal to 0. In the point form, also known by the differential form, we can denote it as divergence of b is equal to 0 here. Divergence of b is equal to 0, because unless and until the magnitude of current in the current element is not changed, so there it will not be any kind of expansion or contraction into the magnetic field. So therefore it will be a constant, no expansion, no contraction. So divergence of B is equal to 0 here. So I hope the concept of magnetic flux density I have made it very much clear to you people. Now for practice purpose, let us have a problem statement. The first problem test statement. So that will deal with the magnetic flux density computation here, and it will also link up the previous topic that we have already covered, magnetic field intensity. So here it goes, the problem statement. The problem statement is a solid non-magnetic conductor of circular cross section has a radius of 2 millimeter. The conductor is inhomogeneous with, we have been provided the conductivity denoted by sigma here. Here it is equal to 10 raised to the power 6 in multiplication to the parenthesis where 1 is added to 10 to the power 6 into rho square here, and this is in terms of Siemens per meter. Now the problem statement continues with, if the conductor is 1 meter in length and has the voltage of 1 millivolt between its end, find. We have total two parts to find as a solution to this problem statement. So in the first part, here we have to find capital H inside the conductor here, and in the second part we have to find magnetic flux inside the conductive material here. So this is our complete problem statement here. The situation in this particular problem statement we will make it clear with the help of one illustration, so that you just see. So here we have taken the help of the horizontally oriented the y-axis, the vertically oriented z-axis, and mutually perpendicular to both of these, that it is x-axis here. And here we expect a solid non-magnetic conductor of circular cross section having a certain radius as mentioned in the problem statement. So here we consider a conductive material having a cylindrical shape here. So a solid non-magnetic conductor of circular cross section has a radius of 2 millimeters here. So let us have the representation of radius with the help of this line segment here. So here you can have the marking 2 millimeters here. So now in continuation to this situation here, the conductivity value is provided in this material here. See, the conductivity is given by sigma is equal to 10 to the power 6 in multiplication to the bracket where we have 1 plus 10 to the power 6 rho square, and this is represented in terms of, we have Siemens per meter. Now as the body of this conductor is cylindrical shape, now the convenience it will be there to have the things represented by the cylindrical components here. We have learned the cylindrical coordinate system, and yes, I hope one question is there. Heath Naik, when we change polarity of the current, will the electromagnet repel the material? See, as far as the current component is there, it is no question of the polarity here. When you have a charge, so the charge will have the polarity of either positive or negative here. There it will be a change into the direction of current here, the current flow direction if you reverse. So your question is, will the electromagnet repel the material here? See, of course, whenever there it is a certain coil here that is having a flow of current, and if you have in the surrounding electromagnet here, so there it is the interaction between the two. So depending on whether they are having some like polarities as you say or unlike polarities, so there it will be the force of interaction. It may be the force of repulsion or it may be the force of attraction here. So I just continue with my problem here. So here it is our conductor that is carrying the current here, a solid non-magnetic conductor of circular cross section having a radius of 2 millimeters here. Now if the conductor is 1 millimeter in length, so in this illustration you consider that this much of length of this particular conductor is equal to 1 millimeter. Yeah, welcome Hitnaik. And this much of dimension is equal to 2 millimeters here. And inside, as I was discussing, it is quite convenient to make the use of the cylindrical component representation here. So as per as the radius of the cylinder goes on changes, the conductivity also changes here. That it was the expression of conductivity. See, sigma is dependent on rho here. So rho can be a notation in general to represent the resistivity here, but you keep one thing in mind there, that resistivity and conductivity both are inversely proportional to each other. So don't get confused. Rho here, it is representing the radius of the cylinder here. So as the value of the radius of the cylinder changes, as you are just nearby to the center or nearby to the periphery, you just put that particular distance of that point from the center of this conductor, you will find the conductivity. So the conductivity is not uniform, it is not homogeneous, it is inhomogeneous as per the problem statement. Now one more thing it is there, to this conductive material there should be a certain supply so that the current flow will be there, and then there it is magnetic field in the surrounding. So if we have, as per the problem statement, a voltage of 1 millivolt between its end, so to the top end, so either we have the application of positive terminal of the battery, and to the negative end we have the to the bottom end we have negative end of the battery. So there it will be a flow of current. So now in this particular situation we have been provided the voltage that is applied in between these two ends, that it is 1 millivolt here, and using this much of information we are asked to find the total magnetic field intensity inside the body of this material, and then the total magnetic flux inside the conductive body here. So first of all we will have a solution for magnetic field intensity capital H inside the conductor. So let us solve for it. Now very first of all what we do, as we require capital H, and the provided thing in this particular problem statement is the only one parameter except the dimensions here is the conductivity. We can have the use of conductivity with the help of the electric field intensity, and then we shall go for the magnetic field intensity here. See here, for any material at the two ends, if we are applying a certain voltage, so if we know the voltage applied and the dimension here, so that time we can find the electric field intensity that is existed in that particular material here. So in general we can denote it as electric field intensity by capital E, that is equal to the voltage applied, in general we denote it by V0, and that is divided by the dimension, that it is equal to small d. And you see here the application of the polarity is as such, the current flow is there, and here the electric field intensity is also there to represent the direction, that is considered to be in the positive z axis here. So now if we have the substitution of the dimension here, see here the dimension of this conductor is 1 meter here, and of course here we have the length denoted by 1 meter, and the voltage denoted by 1 millivolt here. So milli stands for 10 raised to power minus 3. So the substitution here will give us the value of electric field intensity as 10 raised to the power minus 3 into Az, and this is of course to be denoted in terms of volts per meter here. Now here we go, as we have the electric field intensity now we have to make a computation of the cross sectional current density, that we usually denote by the letter capital J, which is just the multiplication of sigma, the conductivity provided in the problem statement, and the electric field intensity. So here we represent J is equal to sigma E. See, J is equal to sigma E is also sometimes considered to be the Ohm's law into the wireless medium here. So E is showing us the electric field intensity measured in terms of volts per meter. J, it is measured in terms of ampere per meter square. So ampere is the unit of the current. Here it is amperes per meter square, that it is the measurement of the J, whereas E is here volts per meter here, and sigma is the conductivity. So voltage parameter here it is in terms of E, current parameter here it is in terms of J here. So this is the most important equation, simply the Ohm's law you can say, so that it will switch you from the quantity associated to the charge, that is representing the electric field, to the current, that is representing the magnetic field here. So now we have already the sigma provided in the problem statement and the capital E just computed in the above step here. So we can make the substitution and just find the value of the capital J. So here we go. So we obtain capital J is equal to 10 raised to the power 3. In multiplication to the parenthesis we have 1 plus 10 raised to the power 6 multiplied to rho square. The parenthesis is completed, and here it is the direction of the J, that it is equal to AZ, the positive direction of the Z axis. And see, J it is measured in terms of amperes per meter square. Now in the part A of the problem statement we require capital H. Now how to use capital J to determine the value of H, the magnetic field intensity? So the thing is simple. One of our previous topic that we have dealt before, that it is Ampere circuital law. By using the Ampere circuital law, we can have the circulation of the path for the radius value denoted by rho, and a center that is considered along the x-axis, z-axis here, and the perpendicular direction to this particular axis. Here we can have the relation, the closed line integral h bar dot of dl bar in terms of 2 pi rho into h phi. See here, rho, if it is considered the radius here, so rho is the radius. For any circular shape, if we have a radius and we are asked to determine how much periphery the circular path is covering, so we just have a simple formula, the radius denoted by small r, the circumference, that is the periphery of the circle, is equal to 2 pi r. So here we denote it by 2 pi rho, and here we multiply with the h component, and as the circulation is along the phi direction considering the cylindrical coordinate system, so that time here it will be nothing but the closed line integral h bar dot of dl bar here. So this we also can express in terms of the cross-sectional current density when integrated over the cross-sectional area. For the conductor, if you take the horizontal cross-section, it will also be of the circular shape, the exact same shape here. So here we denote it as the open surface integral j bar dot of ds bar. Now to have the computation on the left hand side as represented, we can make the use of capital J, that we have to integrate along with the ds here. So here we substitute the capital J from the above step, here we have, and then we proceed here. So here we have the surface integral, that it means the double integral here. The one dimension here we denote the integration 0 to 2 pi. Another dimension here we denote 0 to rho. So 0 to 2 pi is the entire range of the angle phi here. 0 to rho is the radial direction here. So this is the cross section. The surface area is in the horizontal plane here, a circular disc here. So both the dimensions here we have considered, and this integration is over. The dot multiplication of 10 to the power 3 into 1 plus 10 to the power 6 into rho dash square az, with that of az multiplied to rho dash d rho dash and d phi here. So from this expression we can find out the magnetic flux, the magnetic field intensity in the phi component here, that we have to denote by h phi component here, and here it will be 10 raised to the power 3 divided by rho taken out as a constant, the integration 0 to rho over rho dash plus 10 to the power 6 into rho dash cube here into 2 rho dash here. So after integrating and application of the limits, it will be 10 to the power 3 by rho in the square bracket, here it is multiplied to where rho square divided by 2 added to 10 to the power 6 by 4 into rho to the power 4 here. So here it is the expression of the h phi component here, and here we can have the simplification to simply capital H. We have 500 into rho in the bracket 1 plus 5 into 10 raised to power 5 rho cube into a phi. See, a phi is the unit vector directed along the progression of the angle phi in the horizontal plane, which is basically the direction where the magnetic flux lines are circulating surrounding to the current carrying conductor here. And as here it is the magnetic field intensity, it is expressed in terms of amperes per meter, whereas this has been measured inside the conductor, hence the range of rho that we have shown already, that it is 0 to 2 mm here. So this particular answer you can just outline as a solution to part A here. So this is solution to part A of the problem statement here. Now we are going to have a solution to part B here. So I just recall back what it was part B question in the current problem statement. So in the current problem statement in the part B, we have been asked to find the total magnetic flux inside the conductor here. So magnetic field intensity we have determined in the first part A. Now we require the total magnetic flux inside the conductor here. So now the magnetic flux is there in the phi direction. It is a plane in the horizontal orientation, and now if we have the field in the phi direction, a plane that is perpendicular to the capital B representing the magnetic flux density, it will be that in the region that inside, hence we have to consider the rho dimension ranging from 0 it means the point on the z axis, and 2 millimeters, that it means on the periphery of the current carrying conductor here of the cylindrical shape. So rho will be 0 to 2 mm, and the z it will be from 0 to 1 meter, because in the problem statement we have been provided the length of this current carrying conductor here, so that is of the 1 meter. So z value, that upright orientation, we have been considering 0 to 1 meter. Now we require the total flux. The total flux we denote it by the symbol phi. I have already made it clear. For representation of the total flux, we shall denote with the symbol phi here, and we can have the computation of the same just by have the integration of magnetic flux density. Our today's topic title, magnetic flux density, it is denoted by capital B. So capital B dot ds, the dot multiplication of the two vector quantities first of all we have, and then integrate on both the dimensions, that it is the surface integral here. So we require B. We don't have B right now here, but we have H. The relation between H and B I have already provided in the beginning. So B is magnetic flux density, H is magnetic field intensity. Both are related with the help of a constant, that it is mu0. It is permeability of the medium. The value of mu0 also I have shared with you people, that it is 4 pi into 10 raised to power minus 7 measured in terms of Henry per meter here. So we just keep mu0 as a constant outside. B is equal to, we had the relation thereupon, B is equal to mu0 times H, consideration of the free space in the surrounding here. So mu0 we keep outside the integrals. The two integrals here we arrange for the dimension along the z axis. The first integral 0 to 1. The second integral along the radial direction 0 to 2 millimeter. So 2 into 10 raised to power minus 3, a multiplicand here, and this is applicable to, in the bracket here we write 500 rho plus 2.5 multiplied by 10 to the power 8 into rho cube here, d rho dz here. So when we perform the integration over this particular bracket here, we come to have the value in terms of 8 pi into 10 raised to power minus 10. So this is the total magnetic flux. So the magnetic flux is measured in terms of Webers here. That is why we provide the SI system of unit at the end beside the magnitude value here. So this is in terms of Weber here. And here if we have pi is equal to 3.14 here, so that time by using the value of the constant pi here, we can also get it to the form 2.5 into 10 raised to power minus 9 Webers. So this is nothing but the nano here, 2.5 nano Weber. So this way the solution to the part B of the problem statement also we have done here. So pi is equal to 2.5 nano Webers. This is our answer for part B here. Part A also we have answered for magnetic field intensity, and for the total magnetic flux also this is the answer. So this way the first problem statement is covered here. So after a practice of the first problem statement, let us have another problem statement. Now in this another problem statement, we will have a rigorous practice to have computation of the total magnetic flux, because in the first part of the previous problem statement we had a computation of the magnetic field intensity, and then utilizing that value we had gone to have computation of the total magnetic flux here. So here it goes for the second problem, where again the conductor is of the cylindrical shape. The problem statement starts with the cylindrical shell defined by rho greater than 1 centimeter and less than 1.4 centimeter consists of a non-magnetic conducting material and carries a total current of 50 ampere in the AZ direction. Find the total magnetic flux crossing the plane. Phi is equal to 0 and Z is greater than 0 but less than 1. Whereas we have the three conditions for the parameter rho here. In the first part we have rho ranging between 0 to 1.2 centimeter, and thereupon we have in the part B rho ranging between 1 centimeter to 1.4 centimeter, and in the last rho is ranging between 1.4 centimeter to 20 centimeter. Now just read the problem statement thoroughly and get the situation to your mind. Now as I said, there it is the cylindrical shape again here, but it is not a complete solid cylinder here. Here we have a cylindrical shell here. Cylindrical shell, it means you can imagine a cylinder inside a cylinder, and inside the cavity there it is, which is hollow here. Now see, for this particular shell, the dimension it is provided in terms of the rho. See, for a complete cylinder we have to range from rho is equal to 0, which is the point on the z-axis, if you consider z-axis to be the central axis of that particular cylinder here. See, it is from 1 centimeter to 1.4 centimeter, and inside there it is a non-magnetic conducting material that carries a total current. Magnitude it is provided to us, and the direction also it is the positive AZ direction. What we have to do? We have to find the total magnetic flux crossing the surface, crossing the plane. So plane has to be defined by the three parameters here. The one is phi is equal to 0. So when we have the z axis, y axis and the x axis like this, mutually perpendicular to these one. So the phi angle we measure right from the positive x direction towards the positive y direction, and the same direction of measurement of the angle phi is carried forward throughout this particular plane. So this is the measurement of angle phi here. So when we have phi is equal to 0, phi is equal to 0, it means we have limited the value of phi to a fixed value 0, but not limited the other two parameters. The other two parameters, if you say these are z and the rho, they are infinite. So it means in this particular direction, in this particular diagram here, if we have again the three axes here, so phi is equal to 0, it means a plane that is aligned along the positive x direction by one end here, by one edge here, I can say. So this is the positive x direction by this particular edge, and this is the another edge that is along the positive z axis. So xz plane is nothing but the phi is equal to 0 plane. Okay, or also we can call it to be y is equal to 0 plane when considering the rectangular coordinate system here. So this is what the plane. I am just showing you only one quadrant here. This plane is also there in the negative side of both the x and z dimensions here. Now in this plane we have to limit the value of z from 0 to 1. So z is equal to 0, it means at the level of origin, at the unit of 1. So thereupon you have to carry on a line that is intersecting the z axis into z is equal to 1. And what is about the rho? Rho is the distance that a point has away from the central z axis. Okay, so when you have a limitation of it with 1.2 centimeter, so this is just this way here, and from 1 centimeter to 1.5 centimeter, 1.4 centimeter, this way you can have the distance. So I suppose it is better to draw another diagram that will give you the complete idea here. So just I am showing you a cylindrical shell. Cylindrical shell, it means a cylinder inside cylinder, and the inside cylinder is hollow there. So see here. So you see the cylinder that has been shown with the help of the yellow color, and it is hollow inside, that is represented with the help of the white colored cylinder here. So this is what the situation here we have, and in the part A, B and C we have a variation of the rho values, and with the help of the definition of such a plane here, we have to just make a computation for the total magnetic flux crossing that particular plane here, so that it will be a plane like this, and through this plane how much magnetic flux line will be crossing, that we have to compute, and that it will be the solution to the question here. So now let us have part A to be solved, where rho is ranging from 0 to 1.2 centimeter. Rho is greater than 0, but it is less than 1.2 centimeter. So very first of all, for determination of the answer as the total amount of magnetic flux crossing the plane as defined, we need to find the parameters capital J, that is the cross sectional current density. Then using capital J we can make a computation of capital H, that is magnetic field intensity, and then using the magnetic field intensity we can have the last computation of the magnetic flux density, and integrating it, it will be the total magnetic flux. So let us first of all find out capital J from the given value. See, we know here how much amount of current is flowing on the cylindrical shell. See, the problem statement gives you the information that this cylindrical shell is carrying 50 amperes of current in the positive AZ direction. So in the upwards direction there it is flow of the current. If I get back to the diagram here, so you see here, whatever the yellow color it is there, here also you have to consider the completion here. So this particular portion is a cylindrical shell, and it is carrying 50 amperes of current in the upward direction, that it is the meaning here. Now we just put 50 into the numerator and divide it by the cross sectional area. While having the cross sectional area of the cylindrical shell here, we have to subtract the cross sectional area of the inside cylinder from the cross sectional area of the outer cylinder. So that subtraction here we arrange. See, the area, it will be by pi r square. So r will be in general a notation for radius for a circular shape here. This is our rho here, rho representing the radius in the cylindrical coordinate system of representation here. So here we do 50 amperes divided by pi. Inside the square bracket we have the difference. First term is 1.4 into 10 to the power minus 2, which is squared. The second term, which is to be subtracted from the earlier one, that it is 1.0 into 10 to the power minus 2, which is also squared here. The direction of flow of current we have provided AZ, and this calculation simplifies to the value 1.66 into 10 to the power 5 AZ, and as this is the cross sectional current density, the magnitude of the current divided by the surface area. The surface area here we denote in terms of meter square. So ampere per meter square is the unit here. Now, from the knowledge of this cross sectional current density, we have to go for calculation of the magnetic field intensity. So for determining the magnetic field intensity, we take the help of the Ampere's circuital law. According to the Ampere's circuital law, the total amount of current enclosed inside a closed loop we can determine just by having the integration here. So that thing we can denote the I enclosed. Here I show on the right hand side I in the suffix ENCL for representing. This is the enclosed current inside a closed loop. This is the closed loop. Okay, closed counter path here. So this is nothing but the periphery of the path, that it is 2 pi rho. Rho is the radius of this closed loop multiplied by the h, that is along the pi component, hence h pi here. So this we can express to as the surface integral of j bar dot of ds bar. So j bar just now we have computed in the above step. The answer here you see 1.66 into 10 to the power 5, the magnitude here. So that we put in this place j bar dot of ds bar. The ds bar for the circular cross section, here we denote it by rho dash d rho dash into d phi here. Okay, the change along the radial direction, that it is d rho, and the change along the angle phi direction, that it is rho dash multiplied to d rho. That the basic we have already covered in the first chapter here. So this we have to integrate over the two dimensions. The first dimension for the angle phi 0 to 2 pi. The second dimension over the radial direction. As this is for the cylindrical shell here, we have to go for 10 to the power minus 2 to that of the rho here. Now this integration on the right hand side will give us the value of the capital H. The capital H, that it is the magnetic field intensity here. So here it implies to H phi. H phi is equal to 8.30 multiplied to 10 raised to the power 4. This is further multiplied to the ratio where numerator is rho square minus 10 to the power minus 4 divided by rho, and this is in terms of ampere per meter here, where the range of rho here we have specified for the cylindrical shell, that it is greater than 10 to the power minus 2 meters but less than 1.4 into 10 to the power minus 2 meters here. Now this way we have obtained the magnetic field intensity. So using the magnetic field intensity we can determine the magnetic flux density. So the relation here it is B is equal to mu 0 times H, unless and until it is specified a specific material with the values of the sigma, epsilon and the mu, because sigma is the conductivity, epsilon is permittivity and mu is the permeability. These are the three characteristic parameters to describe a certain material to be a conductive, non-conductive, semi-conductive and so on here. So here we can directly take it to the value of mu 0, considering it to be a free space here. So just multiplying mu 0, the constant 4 pi into 10 raised to the power minus 7 Henry per meter to the value of magnetic field intensity in terms of ampere per meter, it will give us the magnetic flux density capital B. So capital B is equal to, it becomes 0.104 times the ratio of rho square minus 10 to the power minus 4 to that of rho here, and the direction of this magnetic flux density is given by the unit vector A phi here, and the magnetic flux density, the total amount of magnetic flux divided by the surface area of a certain plane. So it means Weber per meter square, as you see the SI unit we have shown here. Yes. Now, after determining the magnetic flux density, now it is very simple to have the computation of the total amount of the flux here. So the total amount of flux for the part A, that is designated by phi is equal to 0, z ranging between 0 to 1 and rho ranging between 0 to 1.2 centimeters. We have phi, the total flux is equal to the integral, surface integral, that it is double integral b bar dot of ds bar. The dimensions here we put on the integral notation. The first integral for 0 to 1, the second integral 10 to the power minus 2 to that of 1.2 times 10 to the power minus 2. This is over 1.104 multiplied to the square bracket that has a subtraction rho minus 10 to the power minus 4 by rho, and there it is d rho dz outside, and here we just perform the integration to be computed here. We have 0.104 multiplied to the square bracket that has 1.2 into 10 to the power minus 2 bracket squared minus 10 to the power minus 4 divided by 2 minus the second term here we have 10 to the power minus 4 ln of 1.2 divided by 1.0 here. So now this computation gives us to the value 3.92 into 10 to the power minus 7. You can have a computation on your calc here, and this has to be of course expressed in terms of Webers here. Weber is the SI unit for representation of the values of the magnetic flux here. Now the multiplicand 10 raised to power minus 7 we can observe for 10 to the power minus 6 in terms of micro here. So that is why this value I expressed just by 0.392 micro Weber here. So you can outline this particular answer. Phi suffix A is equal to 0.392 micro Weber. This is what the solution to part A of the problem statement here. The second problem we are going on, and this is what the solution here we have obtained here. There it is, Rahul Kumar Reddy Molaka. Hello. If you have any doubt to this particular problem, you can ask me. See, this particular problem statement is having the three sections, part A, B and C to be solved for. I have just a solution to the part A here, and now part B I am going to solve here. Now I just recall back to the part B problem statement. The same procedure here we have to repeat, just the change into the range of rho there it is. Instead of having the rho ranging from 0 to 1.2 centimeter, we have the rho that is greater than 1 centimeter but less than 1.4 centimeter. And here also we have to make a computation of the total amount of the magnetic flux crossing this particular plane. Now see here, for computation of the total amount of magnetic flux here, we require the magnetic flux density. So whatever the steps we have carried out in the first part are need not to be repeated here. The cross-sectional current density denoted by capital J in terms of amperes per meter square, it will be the same. The magnetic field intensity in terms of the amperes per meter denoted by capital H, it will of course be the same, and the magnetic flux density will also be the same. Only we have to have the integral of b bar dot of ds bar on the new dimensions as provided in the part B of the problem statement. So here we go, we represent the total amount of magnetic flux to be as a solution to the part B, denoted by phi suffix b here, as you see, small b, and here we express in terms of the surface integral b bar dot of ds bar. Surface integral means a double integral here. So the two dimensions, the first dimension here we put the limit on integral sign 0 to 1. The second integral we put the limits 10 to the power minus 2 to that of 1.4 into 10 to the power minus 2, and here we have to integrate from the previous part. We can substitute it 0.104. In the square bracket we have rho minus 10 to the power minus rho divided by 10 to the power minus 4 divided by rho. The square bracket is completed, and here it is multiplied by d rho dz here. Now 0.104 we can keep as constant and outside, and to the rest of the part we can apply the integration here. So this will give us 0.104 multiplied to the square bracket. Inside the bracket the first term is 1.4 into 10 to the power minus 2 squared minus 10 to the power minus 4. This is divided by 2. Minus, we have the second term expressed as 10 to the power minus 4 ln of 1.4 divided by 1.0 here. So all the values are there. We just have to form the answer for the natural logarithm of the ratio as represented in the second term here, and then just a multiplication, division and the subtraction here. So this will give us the value. If you compute on calculator, it will be 1.49 into 10 raised to the power minus 6, and as again this is the magnetic flux, we have to express it in terms of Webers here. 10 raised to the power minus 6, here you see a multiplicand that we can absorb by representing the flux in terms of micro Weber here. So here we go, 1.49 times, not times, 1.49 micro Weber. Here it is the answer to the part B here. So this way the solution to the part B is also done here. Now there it is part C. In the part C, rho is greater than 1.4 centimeter, but it is less than 20 centimeter. So if you see this range of the parameter for rho here, this is completely outside whatever the current distribution here we have in the cylindrical shell as defined for rho greater than 1 centimeter and less than 1.4 centimeter. See, the given value of rho is just starting from 1.4 centimeter where the current distribution has ended here. So therefore here we require the magnetic flux density in this particular case, which will be a modification by the use of the Ampere circuital law that we have applied in the part A of this particular problem statement here. So here we write for the outside of the current distribution, so capital B, in the suffix we write OUT out, and this is given by, here we write 0.104 as it is, and here we describe it as the numerator 1.4 into 10 to the power minus 2 bracket squared minus 10 to the power minus 4 simply, and this difference is divided by rho, the unit vector to represent the direction. Here it is a phi. So this will simplify to the representation 10 to the power minus 5 divided by rho into a phi, and as this is magnetic flux density, it is expressed in terms of Weber per meter square. Now what is the total magnetic flux? We have to integrate the value that we have determined. So the total magnetic flux as a solution to the part C, here we denote it by phi suffix C, and this is equal to the double integration, surface integration. So the first integral we take from 0 to 1, the second integral 1.4 into 10 to the power minus 2 to 20 into 10 to the power minus 2. See, 10 to the power minus 2 we have taken as the multiplicants represented by centimeter here we have. So we have to get all the parameters covered in the same unit. So here we have to shift for the SI system of unit representation centimeter to meter. We have to put centi to be 10 to the power minus 2 here. So it will be applicable to 10 to the power minus 5 divided by rho into d rho dz. So by the next step, we solve the integration and we get it to the form 10 to the power minus 5 ln of natural logarithm of 20 divided by 1.4, and this results into, if we take the logarithm value, 2.7 into 10 raised to the power minus 5. So this is in terms of Webers. The multiplicand 10 to the power minus 5 we can absorb if we have representation as, instead of 2.7 we write 2.27. So if we have a shift of the decimal point to the right hand side, there it will be 10 to the power minus 6 in the multiplicand. So 27 into 10 to the power minus 6, we can write it to be 27 micro Webers here. So this is what the solution, and this way we are having the answer to the part C, the total amount of magnetic flux that is crossing the given plane defined by phi is equal to 0, z greater than 0 but less than 1, and the rho which is greater than 1.4 centimeter but less than 20 centimeter. So in this particular case we have the answer to be equal to 27 micro Weber here. So this way we have a solution to the part C of the problem statement as well. So in our today's live session we have discussed the concept of magnetic flux density. We have also related to whatever we have seen in the electrostatics, the corresponding quantity, electric flux density, electric field intensity. Here magnetic flux density, magnetic field intensity we have dealt with. Also the computation we have made with the help of determining the cross-sectional current density denoted by capital J. So this way I hope the concepts related to magnetic flux density are clear to you people, and we shall meet by the next week with another topic. Possibly I will be taking the boundary conditions in the next session. Thank you.